Hi class, this first chapter is just about oceanography and science in general. The map is just a funny take on what the Earth would look like if a fish drew the map of the Earth. We are living on a planet that is 71% ocean. So it's mostly ocean. We tend to think of the Earth as the Earth, but it's really the ocean. Takes up most of the surface of the Earth. Of that 71%, 80% of that is in the southern hemisphere. So we're continent heavy at the top of the Earth. In the bottom part, the southern hemisphere has most of the open ocean spaces. You can see that if you spin a globe around and look for ocean basins. So why should we study oceanography? So you're taking oceanography either because you're really interested in the ocean, maybe you are an education major or a geology major, just trying to get through those science electives here in your gen ed studies. So here are some real reasons why studying oceanography is a good idea. Well, if we want to understand life and where it began and where it's going, we go to the ocean basins because 4 billion years ago, life started in the ocean basins. The ocean drives and regulates Earth's climate. We have a whole chapter on circulation of water around the globe, and the water moving around the globe, cold water moving down from the poles and warm water moving up from the equator, makes life on Earth possible or comfortable in the mid latitudes and a little bit higher. So we'll see how parts of the Earth don't get too hot and other parts don't get too cold because of the movement of and circulation of seawater. The key to plate tectonics was found on the ocean floor. So a chapter coming up is about plate tectonics, and we didn't have a total understanding of the theory of plate tectonics until the early 70s, late 60s, early 70s, and that knowledge base that really solidified it as a unifying theory in geology came from our understanding of the topography of the ocean basins. So earthquakes and volcanoes and all that jazz, we learned about it from figuring out how ocean basins jive with plate tectonics. An important source of food around the world. Not everybody loves seafood. I do. I love sushi. I love fried shrimp. I like going out fishing with my family. We go diving for lobsters in the Keys every summer. Christmas. So eating food from the sea, I guess I would consider it a luxury for people like us, but many people subside off of the bounty of our oceans. So it's an important source of food. Even if you don't like seafood, I know it's an acquired taste, there are parts of the world that really rely on our ocean basins. Sources of natural disasters. Tsunamis occur in our ocean basins when there's movement on the seafloor. Hurricanes, I know the fall of the year is hurricane season, so you got to be on the lookout for storms cropping up in the Atlantic. There are hurricanes around the world. They have different names like typhoons, but hurricanes are something we need to think of. They're related to heat flow from our ocean basins and flooding. As sea level rises, we can get flooding inland at a high tide. They keep getting higher, right? So we need to think about that and the process that governs sea level rise and our tides. Navigation, exploration. Who doesn't want to go explore islands, right? So there's a chapter coming up about the exploration of our ocean basins. So many people live aboard sailboats. In the olden days, pre-COVID, people went on cruises all the time. So exploring the ocean has always been a human nature. People want to go out there and explore. Navigation, so getting places. These days, flying is so much quicker, but taking a boat somewhere just has a certain allure to it as well. So taking boats and exploring is really a big part of learning about oceanography, the hazards and the circulation. And then lastly, the food web. There's a lot in the news these days about the collapse of our coral reef communities. Ugh. And how they are the basis for the kind of nurseries and diversity in our ocean basins. So we'll talk more about food webs and that circle of life later in the semester. Okay, so our ocean basins, they are part of the hydrosphere. So here's the water of the earth, the hydrosphere, which is fresh water, salt water, frozen water. And so we are part of the hydrosphere. This image here is the first time the planet had its picture taken, and that was in 1972, the year of my birth. Okay, you weren't even here. Okay, so let's look at these spheres. We have the atmosphere for coming in from the top. The atmosphere, and that's the gases around the earth, and we'll talk about the different layers, stratosphere and troposphere, and those spheres, and what they mean later in the semester. The biosphere then is all the life on earth. Certainly in the atmosphere there's life, birds, bats, butterflies, all that. And then the biosphere also goes down into the lithosphere in caves, and the biosphere is a part of our hydrosphere. The lithosphere is that solid outer earth. We use the term lithosphere. It is the crust and the upper mantle, and it's the rigid part of the earth that moves around during plate tectonics on top of what we call the asthenosphere, which is the squishier layer underneath the lithosphere. Okay, solid earth. The hydrosphere, again, is all the water, frozen, salty, liquid, groundwater, all the water in the biosphere. There's lots of water in us. There's water in the atmosphere. Okay, so the pedosphere is the disaggregated material of the earth. So we can use two terms there. We could use the term soil. Soil sometimes implies that it is, we can grow plants in it. But there's another term we can use that is regolith, and regolith is all the loose material on the outside of the lithosphere. The regolith, that's all the loose material on the surface of the earth. So it doesn't necessarily mean that you can grow food in it. It would just be anything, gravel, sand, dirt. That's regolith. The cryosphere is all the ice of the earth. So we think of it like Antarctica and Greenland, but there's other smaller mountain glaciers in the world. And then there's the tundra, and the cryosphere would go into that frozen soil layers like we see in the outback, like of Alaska. So cryosphere is more than just Antarctica. Okay. What is science? Science is making observations and describing the natural world, and then coming up with a hypothesis to explain what we have observed. So we test that hypothesis by collecting data, and then we develop that hypothesis over time. We throw out the hypothesis and start over, or we can edit that hypothesis and continue on with it. Or maybe our hypothesis is proved to be true on the first go round. That's not usually the case. But in the scientific method, then, we would share that evidence and that hypothesis with the public. We would have other scientists verify our experiments and see if they can replicate our data. So scientists build on the studies of their predecessors. So when I do science, I look up the science that's done before me on what I'm investigating, and the scientists that come after me will use my research. Okay, we use the term empirical, this word in bold in the middle, based on, concerned with, or verifiable by observation or experience rather than theory or pure logic. So we can logic our way through things, but we need to have some data and observation and experience to back them up. And that's the empirical part of science. The scientific method then. So when we do science, we are, oh, let me move my face. When we do science, we're going to observe, maybe classify or differentiate. We'll describe, we take notes in our notebooks. That's why probably in a science class in high school, you had a science notebook. We're going to ask a lot of questions. So questioning is a big part of science, and come up with a hypothesis. So we have to have a hypothesis that we can test, rigorously test, not just once, but multiple times. We would test that hypothesis. And if we have a hypothesis that withstands the test of time, it can become a theory, an idea that explains a reoccurring phenomenon or law that has yet to be proven false. That would be like the theory of plate tectonics, where the lithospheric plates are moving around on the asthenosphere. So that's a theory. All right. I still don't have all the answers, but I'm beginning to ask the right questions. So science is really about asking all the questions, just from all different angles. Let's get all the questions asked. We don't worry so much about the answers, because the questions in science, we should be able to do studies to figure out the answers. Yeah, so it develops over time. All right, so let's go through an example. I'm going to turn my face off here of what that would look like. So if we collect a data set that is sea surface elevations, the surface of the water. So I'll just start with 0 is the, this is time. So on the x-axis is time, and 24 is the 24-hour day. And then the y-axis is going to be sea level. So this 0 would be low water, and at the top would be high water, and in the middle would be the mean tide line, the middle of the shoreline, like between the lowest low and the highest high. And this is a graph then of what tides are doing. I just defined it for us, the T and the MTL. So that's what tides are doing, and these are different kinds of tides. This first graph is the diurnal tide, the middle graph is the semi-diurnal tide, and then the lower graph is the semi-diurnal mixed tides. When we get to the tides chapter, I'll go over how those different tides come about. So these are the data sets that reflect the sea surface elevations, the literal surface of the ocean rising into the shoreline, and then the literal surface of the ocean falling away. So if we measure hourly, this is what it looks like. So a hypothesis could be that the sea surface responds regularly to tidal forces. And what are those tidal forces? It turns out it's the moon mostly, and some of the sun. So the theory, so over the course of time then, this hypothesis has stood the test of time, and we haven't been able to disprove that hypothesis. So it's now known as the tidal theory, that the sea surface measurements made worldwide confirm that the response of sea surface, it is the response of the sea surface to tidal forces, and those tidal forces being the gravity of mostly the moon and somewhat the sun. So that's how we do science. What are we going to study in this class? Turn my face back on. Hello. The next chapter is the history of oceanography, and then we'll look at the Earth with those spheres, the lithosphere, and then go to the asthenosphere and the core, and we'll see how and why and the landforms that result from plate tectonics, the unifying theory of geology. we will look at the seafloor. It has that topography to it, and that topography and the location of the sea, of where different geographic locations are going to have different sediments, and then the biological activity will create different sediments. So we'll look at the sediments of the seafloor. Then we'll look at the properties of seawater, physical properties, and then chemical properties. So chemical and physical properties of seawater. We'll look at the atmosphere. Already alluded to how the climate is kind of in part controlled by the oceans and circulation. So we'll see how that plays out. We'll look at movement of the water. So we have waves, those are generated by wind, tides by gravity, and we'll look at tides by the gravitational pull of the moon and the sun. So we'll do that. Then we'll come inland a little bit, like at the connection between the land and the sea, and look at coastal processes, beach processes, and also estuaries, that the brackish waters where fresh water and salt water meet. Then we'll talk about the organisms for 3 chapters: living ocean, plankton, productivity in the food web. So plankton just means that the organisms cannot swim against the current. So this would be like jellyfish. And then nectonic, or like fish, they're swimmers. And the benthic organisms, or the organisms that live on or in or connected to the sea floor, like a starfish or an oyster, right? Not swimming. Nectonic swimmers. And then environmental issues, whether it has to do with pollution or climate change. So we'll look at those as well. And overfishing. We'll cover all the exciting environmental issues. Okay, that's it for today. Thank you very much.